Now we are discussing one problem in this unit. At 298.15 Kelvin and atmospheric pressure, the volume changes if mixing of binary fluid mixture of species 1 and 2 is given by the equation delta V is equals to x1 x2 into 45 x1 plus 25 x2, where delta V is in centimeter cube per mole. At these conditions, V1 is equals to 110 and V2 is equals to 90 centimeter cube per mole. Determine the partial molar volumes in a mixer containing 40 mole percent of species 1 at the given conditions V1 bar and V2 bar. Here, our aim is calculation of partial molar properties, that is partial molar volume of species 1 and species 2. The formulas for calculation of partial molar volumes are V1 bar is equals to V plus x2 into dV by dx1. Similarly, V2 bar is equals to V minus x1 into dV by dx1. So, our aim is first to calculate V by using the given expression delta V. Now coming to the relationship between delta V and V. In previous class, in property changes of mixing, we derived the relationship between V and delta V is delta V is equals to V minus x1 V1 minus x2 V2. By using this given delta V expression, calculate the V first and differentiate V with respect to x1. After that, substitute all values in partial properties expression. Then calculate. That is our aim of this problem. Now, the given data is x1, that is mole fraction of species 1 is equals to 0.4, that is equals to 40 divided by 100 equal to 0.4. Remaining is the species 2, that is 60 mole percent equal to 60 divided by 100, which is equals to 0.6. Given volumes are V1 is equals to 110, V2 is equals to 90 centimeter cube per mole. Then calculate V is equals to delta V plus x1 V1 plus x2 V2. All the values are given here. Then calculate V. V is equals to 7.92 plus x1 into 110 plus 90 x2. Then simplify the V expression. We will get the expression in terms of x1. That is 7.92 plus 20 x1 plus 90. That is equals to 97.92 plus 20 x1. Substitute the value of x1 here. Then we will get the total volume is equals to 105.92 centimeter cube per mole. After that, differentiate volume with respect to x1, that is 20. Then substitute all the values in partial properties of species 1. That is, V1 bar is equals to V plus x2 into dV by dx1. That is equals to 105.92 plus 20 x1 plus 1 minus x1 into 20. Then simplify and substitute the value of x1. Then we will get the value of V1 bar is equals to 125.92. Similarly, calculate V2 bar, that is partial molar property of species 2. V2 bar is equals to V minus x1 dV by dx1. That is equals to 105.92 plus 20 x1 minus x1 into 20. Therefore, V1 bar is equals to 105.92 centimeter cube per mole. Now coming to one more problem. The following equation have been proposed to represent activity coefficient data for a system at fixed temperature and pressure. Ln gamma 1 is equals to x2 square into 0.5 plus 2x1 and ln gamma 2 is equals to x1 square into 1.5 minus 2x2. To these equations, satisfy the Gibbs-Duhem equation. Determine an expression for GE by RT for the system. Now coming to solution. Given gamma 1, gamma 2 expressions are ln gamma 1 is equals to x2 square into 0.5 plus 2x1. ln gamma 2 is equals to x1 square into 1.5 minus 2x2. Here we have to satisfy the Gibbs-Duhem equation. Gibbs-Duhem equation at constant temperature and pressure is sigma xi dmi bar is equals to G. Expand this sigma term for binary species. x1 d ln gamma 1 by dx1 plus x2 d of ln gamma 2 by dx1 is equals to G. Now simplify the gamma 1 expression, that is substitute x2 with 1 minus x1, that is ln gamma 1 is equals to 1 minus x1 whole square into 0.5 plus 2x1. After simplifying this one, we will get 0.5 plus 2x1 plus 0.5 x1 square plus 2x1 cube minus x1 minus 4x1 square. Therefore, ln gamma 1 is equals to 2x1 cube minus 3.5 x1 square plus x1 plus 0.5. Similarly, calculate ln gamma 2. That means substitute x2 with 1 minus x1. Therefore, ln gamma 2 is equals to minus 0.5 x1 square plus 2x1 cube. Then differentiate ln gamma 1 expression with respect to x1. That is 6x1 square minus 7x1 plus 1. And differentiate ln gamma 2 with respect to x1 is equals to 6x1 square minus x1. Now substitute in equation 1 is equals to x1 into d of ln gamma 1 by dx1, that is 6x1 square minus 7x1 plus 1 plus x2 into 6x1 square minus x1. After simplifying this one, we will get G, that is 6x1 cube minus 7x1 square plus x1 plus 6x1 square minus 6x1 cube minus x1 plus x1 square is equals to G. Gibbs-Duhem equation is satisfied, that is sigma xi dmi bar is equals to G. Now substitute d of ln gamma 1 by dx1 and d of ln gamma 2 by dx1 in Gibbs-Duhem equation. After substituting d of ln gamma 1 and gamma 2 and x1, x2, we will get the value G. We know the expression for G by RT is equals to x1 ln gamma 1 plus x2 ln gamma 2. Here we already calculated ln gamma 1 and ln gamma. Then substitute the values of ln gamma 1 and gamma 2 in G by RT. Therefore, we will get minus x1 cube plus 0.5 x1 square plus 0.5 x1. In this problem, we calculate GE by RT and satisfy the Gibbs-Duhem equation. The given expressions are ln gamma 1 and gamma 2. Then Prove the Gibbs-Duhem equation and derive the expressions for GE by RT in terms of x1. Now coming to one more problem. The following expressions have been reported for the activity coefficients of the species 1 and 2 in a binary liquid mixer at given temperature and pressure. Ln gamma 1 is equals to x2 square into 0.273 plus 0.096 x1. Ln gamma 2 is equals to x1 square into 0.273 minus 0.096 x2. A bit is determine the implied expression for GE by RT. B bit is generate expression for ln gamma 1 and ln gamma 2. C bit is discuss any discrepancy. Can the reported expression be correct or not? The given expressions are ln gamma 1 and gamma 2. Determine the expression for GE by RT and generate expression for ln gamma 1 and gamma 2. And discuss any discrepancy. Can the reported expression be correct or not? We know that G by RT is equals to x1 ln gamma 1 plus x2 ln gamma 2. Already ln gamma 1 and gamma 2 expressions are given in our problem. Substitute the gamma 1 and gamma 2 values here. Then simplify G by RT expression. That is 0.273 x1 x2 square plus 0.273 x2 x1 square. Therefore, G by RT is equals to 0.273 x1 x2. Now coming to B bit. Here we have to derive the expressions for ln gamma 1 and ln gamma 2. Previous class we discussed about the Margulis equations. That is ln gamma 1 is equals to ax2 square, ln gamma 2 is equals to ax1 square. From the A bit, ln gamma 1 is equals to 0.273 x2 square. The coefficient in A bit is 0.273. Similarly, in B bit is ln gamma 2. Similarly, ln gamma 2 is equals to 0.273 x1 square. Now coming to C bit. By the equation from B are not same as reported expression for part A. Therefore, it cannot be correct. Now coming to next problem. The excess enthalpy for a liquid mixture of species 1 and 2 at fixed temperature and pressure is represented by the equation. HE is equals to x1 into x2 into 20 x1 plus 40 x2, where HE is in joule per mole, that is excess enthalpy. Determine expressions for H1 bar E and H2 bar E as functions of x1. Here the given expression HE is equals to x1 x2 into 20 x1 plus 40 x2. Here substitute x2 with 1 minus x1 in given expression and simplify this. Therefore, HE is equals to x1 minus x1 square into 40 minus 20 x1. Therefore, HE is equals to 40 x1 minus 60 x1 square plus 20 x1 cube. This is the partial molar enthalpy calculation. Partial molar enthalpy of species 1 is equals to HE plus x2 into dHE by dx1. Therefore, we differentiate HE expression with respect to x1. That is 40 minus 120 x1 plus 60 x1 square. Then substitute He and dHe by dx1 in H1 bar E. That is, the partial molar excess enthalpy of species 1 is equals to 40x1 minus 60x1 square plus 20x1 cube plus 1 minus x1 into 40 minus 120x1 plus 60x1 square. Therefore, species 1 partial molar excess enthalpy is equals to 40 minus 120x1 plus 120x1 square minus 40x1 cube. Similarly, calculate partial molar excess enthalpy of species 2 by using the formula H2 bar E is equals to H minus x1 into dHe by dx1. That is equals to 40x1 minus 60x1 square plus 20x1 cube minus x1 into 40 minus 120x1 plus 60x1 square. Therefore, H2 bar E is equals to 60x1 square minus 20. Now coming to one more problem. The volume change of mixing is in centimeter cube per mole for the system ethanol methyl ether at 298.15 Kelvin is given by the equation delta V is equals to x1 x2 into minus 1.026 plus 0.22 into x1 minus x2. The given V1 is 58.63. V2 is 118.46 centimeter cube per mole. What volume of mixture is formed when 750 centimeter cube of species 1 is mixed with 1500 centimeter cube of species 2 at 298.15 Kelvin? What would be the volume if an ideal solution is found? Finally, we have to calculate volume of ideal solution. Coming to solution. First of all, we have to calculate number of moles of species 1 and number of moles of species 2. Then we have to calculate the total number of moles. N is equals to N1 plus N2. Initially, we have to calculate N1 by using 750 by P1. That is 12.79. Similarly, calculate N2 equal to 1500 divided by V2. That is equals to 12.66. After adding, we will get the total number of moles. That is equals to 25.45. We know the expression for V is equals to delta V plus V1 x1 plus V2 x2. Therefore, V is equals to x1 into 1 minus x1 into minus 1.026 plus 0.22 into 2x1 minus 1 into 2x1 minus 1 plus x1 into 58.63 plus x2 into 118.46. That is equals to minus 1.026 into x1 plus x1 square 1.026 plus 0.4x1 minus 0.44 x1 square minus 0.22 x1 plus 0.22 x1 square plus 58.63 x1 plus 1 minus x1 into 118.46. That is equals to 0.806 x1 square minus 67.91 x1 plus 118.46. After substituting x1, we will get the volume, that is 88.23. Therefore, total volume is equals to volume into total number of moles. That is equals to 88.23 into 25.45. Therefore, total volume is equals to 2245.45 centimeter cube per mole. Then we have to calculate the total volume of ideal solution. We know the ideal solution formula PID is equals to sigma Vi x. That is equals to, for binary species, v1x1 plus v2x2. Then substitute the v1 and v2 values and x1 value. Then we will get the volume of the ideal solution. That is 88.43 centimeter cube per mole. Total volume of ideal solution is equals to volume of ideal solution into number of moles. That is equals to 88.43 into 25.44. That is equals to 2250.54 centimeter cube per mole.